Hello and welcome to Is IP Really Better Than SDI? The latest in our series of educational videos from IET Media. IET Media is the IET's technical network for engineers involved in all forms of media. My name is Russell Trafford-Jones and I'm pleased to be joined today by Ed Calverley. Ed has 20 years of experience working across a variety of roles, from playout digitization, then lecturer for trainee engineers, both at the BBC. Later, he led innovation in channel and the box solutions at Omnibus, now Grass Valley, and Oasis. So nowadays, it's no surprise that he's just as comfortable consulting with broadcasters as he is training them. And we're very pleased to say that he's here today to do just that for us. Thanks, Ed. How are you doing?
Great, thank you, Russell. Really good to be here.
It's great to have you here. I guess, given that you work with people with IP, you train people in both IP and non-IP topics, that a lot of what you'll be talking today about is coming off the back of what people have been asking you or have said or have been confused about.
Yeah, I mean, I've been across IP from quite early on in the, I was involved in some of the early NMOS interops whilst I was at Suitcase TV, looking at, uncompressed video over IP. So I've kind of worked at the front line of that, trying to build systems to do that. Been involved in lots of the interop sessions at IBC and NAB. And then, yes, I moved into the training side, and you come in touch with a whole different range of people when you start training and talking about it from that aspect, and picking people's brains on projects and a little bit of consulting on projects. So I've got quite a bit of experience on IP, and today I'm going to try and share some of that with everybody.
That's cool. That'll be good. I mean, I spent some time manning part of the IP showcase wall at NAB, and I was struck by how many people just come up and basically say, "So, is this a good idea?" And some people, they're genuinely looking for validation. They want some sort of guidance. They don't know, because they look at what they've got in their facility. They look at the fact they've got to keep it all running. But they know they've got to invest. They know that there's a lot of people saying a lot of stuff about IP, and there's uncertainty. And so I think this is going to be really good to help people put into perspective IP versus non-IP, what's a good idea and how to go about it.
So today we're going to look at, is IP really better than SDI? Lots of people have got lots of views on this, and you've probably heard many presentations before. So let me outline my aims for what I'm going to cover today. Most importantly, I don't want to repeat the obvious. There's many presentations out there about IP, so I want to say something new. Importantly, I do believe IP is the future, but it's important that you realize it comes with compromises. And it's, therefore I want to kind of explain what some of those compromises are and highlight them so that you don't just get distracted by standards. It's important to understand what really matters to you as broadcasters. Many of you in broadcast will have seen this at various trade shows. It's a bit old now. This was Synergy's marketing. I think it was way back in 2016. Really, I don't think personally that SDI is ever going to die. I think certainly IP is the future, but it's important to understand what we mean by that. SDI's certainly got its place and will be around for a while. So I'll mention that towards the end of the session. Firstly, though, I wanted to kind of focus on SDI. It's often just used as a quick three-letter word, but not a lot of people necessarily know the detail. So it's important to clarify what actually is SDI. And to do that, I'm also going to highlight how it differs from HDMI, which a lot of people are now much more familiar with because we all use it at home and with our PCs and things like that. Importantly, SDI is a fixed resolution unidirectional signal. It is just what it is. The signal's traveling down that wire. Is just what it is. It's, it's there. Plugging it into something doesn't change what it is. Unlike HDMI, which has bidirectional communication to figure out what the display can support in terms of resolution and whether or not HDCP security is enabled, so that you don't even get pictures on HDMI unless it knows it's safe to do so. SDI is a really simple signal. It is just a single voltage on a coaxial cable, so ones and zeros, whereas HDMI's got multiple conductors. That in itself leads to the reason why it's perfect for broadcast facilities, in that we can run SDI over much longer distances, and we can install it exactly where we want it to be, pull bundles of cables through walls, much simpler and terminate them in the back of a rack very easily. That's not possible with HDMI. And of course, because it's a very simple signal, it can be split and fed to multiple downstream devices. And that's not really something a signal like HDMI was designed for. So how do we route SDI around a facility? We do that with a router. And a router is simply a device that forwards a source to multiple destinations, or even just one destination. We sometimes refer to those as being cross points. These are how I've kind of showed it there, a little cross connecting a source to a destination. And you'll also hear the term matrix being referred to. These are all the kind of interchangeable terms. So some things to highlight: signals are reclocked as they go through this router, which means that, you know, if you could go 80 meters down a coaxial cable, you get to the router, you can go another 80 meters out of the router. It's important when you see kind of reclocking that you don't get confused with resynchronizing it. A lot of people see that a router has a reference signal input to it and think somehow it's going to resynchronize the video. If you don't understand that, don't worry too much, but it's important to understand you have synchronous video across a broadcast facility, and the reference signal doesn't do that. The reference signal tells the router when to switch, so it makes sure it switches at the top of the frame so that every time you do a cross point, it always switches in a consistent way. Some routers do offer clean switching where they will actually retime things, and again, there's some analogies there to some IP systems, but yeah, at a simple level, it is a very basic device. So you'll often hear people refer to routers, or particularly when they're talking about IP switches and how they can equate to an SDI router, they might talk about some numbered squared. Essentially, when we're talking about how big a router is, we kind of say 8 by 2 or 256 by 256, but that's a mouthful to say. So we say 256 squared. It just tells you how many inputs and outputs we've got in the router, what the capacity of it is. And that's very fixed. If you buy off-the-shelf routers, you may buy ones with very fixed definitions. You know, something like a little Blackmagic router has a limited number of spigots on the back. It does what it does. Larger facilities will always have a modular router. Modular routers are good because obviously you can change the cards that are plugged into them to add more capacity for inputs, outputs, potentially some conversion, audio shuffling. It's not just about routing in these large frame routers. They'll also have hot pluggable power supplies and things like that. And this is the thing we're replacing with IP. Source and destinations in an SDI system, lots of cable. And it's dedicated, it's unidirectional. If you want to get from an output of a camera CCU to a router, or from a router to a monitor, there has to be a dedicated wire pulled in specifically for that purpose, you know, across the building. It's a very costly way to kind of install systems. So as a result, it's typically permanently installed because it's, you know, it's not really practical to go rearranging things once you've got kind of operations into the building. Spare capacity on a router is often exposed so that you can plug up temporary equipment. That's quite common on a cable termination point, a row of BNCs in the back of your rack, or even in the front of your rack on some kind of jack fields. And it's quite common in an SDI facility to find distribution amplifiers. These are a DA. If you hear someone talking about a DA, it's just a glorified name for a splitter. You know, it allows us to not waste our precious router destinations to feed two monitors when they'll always display the same thing. Just stick a DA in there, and then it's a much cheaper way of achieving what you want. It might also be used to kind of feed sources to multiple devices. So you might, all of certain inputs into a router, you might kind of DA them to feed also to a multi-viewer or something like that. Adding more sources can get costly. Depends. We'll talk a little bit more about that because that's a really important point. How do we expand an SDI system? So here's a router. It's got really simple 4 inputs and 4 outputs on a couple of, it's a modular router. So there's one input card, one output card, and we can add sources and destinations to it really easily. We just plug more wires in. Obviously someone has to install those wires, design them, draw up some specifications, do cable schedules, assign numbers. Complex system. We can then add more inputs by adding another input card. We can add more outputs with another output card. Nice and simple. But what happens when you want to go beyond the capacity of the router. That's the big problem with SDI, is when you hit that limit, it gets very costly very quickly. So really easy, let's just stick another router in. It's a really easy thing to say, and people often who haven't got the knowledge of how the signals route through a system don't understand why it can be so costly. Here's an example. I'll try and give you an example without getting too overly complicated. But let's say, you know, we've put our new router in. We plug up our new sources to it, and then someone says, well, I want to see those sources on my existing monitors. Okay, so we need to be able to route those to the new output. How are we going to do that? Similarly, we might want to see existing sources on the new destinations that we've just plugged up. Clearly, this doesn't work. What's the link between them? So in order to do that, we have to rewire the system and free up space. So often, you know, any project involved in kind of installing a new router requires you to completely review all of your inputs and outputs, and essentially move things around and shuffle them around to free up some space on the existing router, so that you can put in tie lines between them, and then put in extra logic for control or management of those tie lines. And on a large facility, that the quantity of those tie lines can be huge, very costly. Yeah, there's ways to kind of minimize the effects. So if there's sources that you want to see on both routers, we can put distribution amplifiers in to split the signal to feed it to both routers, but that can only help so far. Eventually, you're going to ultimately run out. Now, it'd be great. I think every engineer would love to have the biggest possible router frame in their greenfield installation, but that's never the case. Obviously, it costs money to buy a bigger router frame, so you always have to kind of only think 5 years ahead of what you might expand to. And so, but what it means is eventually you're going to hit the limits of your SDI system, which is a big problem. You can only go so far. There's another fundamental problem, and that's when this man walks in. The guy who doesn't understand the detail necessarily. You've just put in all this very expensive SDI kit, and then all of a sudden there's a new standard comes out. If it's not UHD, maybe it's 8K or something else. Your router hardware supports specific formats of video. If a new format comes along, tough. It doesn't necessarily support it. You may be lucky in that there may be some hacks you can get signals through the system, but in many cases, you may be looking at complete replacement of systems. And this is the fundamental reason why new facilities are moving to IP, because they want to kind of future-proof themselves. This is a major problem. So that's clearly a key strength of IP. So let's look at some of the strengths. So here's an SDI router, as we've said, one wire per signal, simple routing. An IP router works at the packet level. And instead of these being continuous voltages on wires, these are packets down an IP-based network. So I've kind of tried to draw them down here as if they were kind of for example, HD video coming down a 10 gig pipe. Most of the time, there's nothing on the pipe. It's only a small packet of data every now and then. It also means that if you're feeding out of that router system, you could feed multiple signals, multiple videos to the same multiviewer or the same vision mixer on a single connection. And that's a huge benefit over SDI. The other huge benefit, perhaps the biggest benefit, is that it's full duplex. So anywhere you put a connection in for IP, you can go both ways. And that can immediately be used for things like PTP timing reference, but it could be in a camera situation. It could be used for return video, so you can see what the vision mix is actually outputting, various uses, but it just makes the flexibility of an IP-based system hugely more, gives you more options than SDI ever could. So what are the standards? I don't want to focus on these in this presentation because there's far too many on the internet already, some of which you might find me presenting. But these are the standards, and these are the kind of numbers that you need to know if you're new to this and you need to start Googling. These are the kind of things you need to search for. It is important to understand these. Or more importantly, it's important to have someone on your team who understands them. If you're doing a project with IP, somebody needs to understand these and understand the kind of technical issues around it. But it's very important as well to not forget about the broadcast side of things. don't just focus on the IP side of it and the technical standards and all that stuff. You must think about what you're actually trying to achieve with this system in a kind of broadcast sense. And that's what we'll talk about a bit more. So with IP, if there are future standards that come along or you want to expand the system, hey, it's just IP. It's an easy statement to make, but that's kind of true. That's the point of it. Just like we said with SDI, it just works. With IP, it's all just IP. It's really simple. As new formats appear, we'll be able to transport them across the network within the bandwidth limitations, of course. So if you've got a 10 gig link and you need to stick 25 gigs of data down it, you're clearly not going to be able to do it. But in terms of using that as it's just a generic data link, and all the kind of standards that will come along will all work with this kind of IP protocol. That's a very low level protocol. Incidentally, I wanted to highlight that a lot of people who are new to IP start thinking about seeing if they can get hold of a 10 gig switch. 10 gig switches are significantly cheaper now. You can buy a small little 10 gig switch for just £150. I bought one recently, a brand new one. But for new proper broadcast installations now, we're really looking at 25 gig connections as standard. So if you're still thinking 10 gig, you're a bit in the past. So adding bandwidth or capacity to a well-designed system compared to SDI is a lot less disruptive. Generally, that's adding additional leaf switches or changing the architecture somewhat differently, but it doesn't really require you replugging lots of equipment. It may require some configuration changes, but again, if it's designed for that in the first place, there really is practically no upper limit to what you can achieve with an IP-based system. Whereas with SDI, there'll always be an upper limit. The fact that they're bidirectional, again, mentioned that earlier, that's quite huge. Every way you've plugged in an IP-based piece of equipment, it's just a generic IP connection. You could take out the camera and plug in a multi-viewer, depending on the bandwidth requirements. You can reuse the cable much more in a straightforward way, and it's probably a fiber rather than a cable, but it's the same thing. The connections are far easier to repurpose. In the SDI world, typically, whenever you kind of took a piece of equipment out of a rack, it was very unlikely you'd reuse the cables unless it was being replaced with an equivalent type of device. With IP, typically you're putting fiber termination points in every area, possibly local to the rack, repatching and replugging things, reusing the infrastructure that you've invested all your money in is much more practical with IP. So this is why all the new facilities are kind of being flood wide with lots of IP connections everywhere and fibers everywhere. So what kind of architecture should you be considering in IP? That's a whole presentation in itself. There's lots of things you need to know about it. And there's another presentation, a webinar that was recorded recently by Gerard Phillips from Arista, which you can find through the link here. And that goes through all of the kind of technical side of the network design that you need to know. Again, that'll explain everything in far more detail. It's well worth a watch. The big takeaway, as you'll hear, obviously Gerard's a vendor of IP hardware. Talk to the vendors, talk to people like Gerard who have been doing this and working on projects for the last few years. They have a lot of experience of this. They are the IP experts. But do remember, they are not necessarily experts in broadcast. They might know broadcast very well from an IP interface point of view if they've been working in it for a while, but they may still miss some of the subtleties of how you actually use the system that's being specified. So just be careful. So some of the weaknesses, and this is the really bit I kind of wanted to highlight in this webinar, because it's the bit I think no one ever talks about. It's almost like the dirty little secret. They want to kind of tell you everything about IP is going to be brilliant and it's the future, and it is the future, but you just need to understand it has some compromises. So why would we move away from SDI when it was so ubiquitous? Everyone uses SDI. Why is it so ubiquitous? It's reliable. Most importantly, it's interoperable. You can buy off-the-shelf equipment and it will just work. It's very straightforward. A lot of work was done early on to standardize the connection and make it just work. And for many years now, since the 90s, we've been able to plug things up and it just works. It's very easy to overpatch infrastructure. So if something goes wrong and you need to kind of take a piece of equipment out or replace it with something else, it's very quick and easy to do that because it's just plugging in wires. It's secure. Hackers can't exploit SDI connections. It is just a voltage going down a wire in a one-way sense. So it's very straightforward. If you've got a studio system that's designed to be a small island with its own SDI router and you need some privacy, you just pull out the U-links that connect you to the rest of the facility. You've got guaranteed privacy. In an IP-based system, can you guarantee that your network is architected in such a way that your signals can't get to certain areas in the building? You can design it if you're careful, but again, it's not as you don't have the reassurance necessarily as pulling some wires out of a patch bay to guarantee that no one can see your signals. So that's why SDI is so liked. So some of the things that it's worth comparing when kind of looking at SDI versus IP. Latency. This is the time it takes signals to propagate through a system. And how that affects things. In broadcast, we've always kind of tried to think of broadcast as a real-time process. In the days of analog, it truly was. With the advent of SDI, arguably there's some buffering that goes in there, but the latency is generally very negligible because it's a matter of lines of video rather than frames of video. And it's also very easy to measure. There's lots of SDI test gear out there. You connect up your external reference and you can kind of work out your offsets. If you need to know multi-frame offsets or AV lip sync offsets, normally people have equipment that's sat around their router that they can plug systems, route through systems, and they can work out those latencies. IP, it's still a little early. The latency varies. Obviously in a specific system, it should be very consistent, you would hope. But just by changing some of the settings, like the receive profile, this is SMPTE 211021, that can change the amount of buffering that is used. So it can kind of cope with dirtier, more variable packets being sent on the network. And that introducing buffering introduces latency, so it can vary. So it's still quite early on, and how best we manage that and how best we track it and measure it across a system it's still quite early days. Something I wanted to highlight that isn't a problem necessarily with IP, but it often gets kind of lumped in with IP, is software-based systems. And this is kind of where the buffering, the larger buffer was designed in the 2110/21 standard. It was originally to cope with software-based senders that are a little bit more variable in their packet timing. With software, you're typically dealing in frames in memory, and therefore you're immediately introducing more processing latency. There are exceptions to this rule. I know that there are some software companies that are doing a lot of work to make proprietary hardware interfaces that get the delay latencies down to sub 1 frame with all their processing, and do it in very stable ways to get the packet timing needed in IP. So it doesn't always go that software is bad. Software is coming, and I'm sure it will get better. There are hardware vendors like Mellanox who are putting drivers into their hardware network interface cards that actually support software processing to kind of adhere to the tight constraints of the new IP standards. So things are coming, but again, latency generally slightly worse than SDI, which may have an impact on your production. A big thing that's become evident on a number of projects I've seen recently is the behavior of the routing. And this is where there really is a massive difference between SDI and IP. And this is where you really need to be aware of it, because it can catch a lot of people out. So SDI routers have been around forever. They are very predictable. You know exactly what they're going to do. If a control system has a serial or an IP interface to it, sends some cross-point commands, it knows on the next top of frame, because it's got a reference signal plugged into it, all of those cross points that were requested will switch, if it's a good router. Importantly, they switch at exactly the same time. There is no difference at all, because that's what the router is designed to do. It's designed to switch at that switching point exactly the same time. In IP, sadly, it's a bit variable. One thing you can guarantee with IP routing, you'll never get two crosspoints switching at exactly the same time, because you're not switching a crosspoint. You're requesting receivers to connect to different multicast flows on the network. Again, you'll learn a lot more about that in Gerard's presentation. Importantly, though, architecturally, different devices work in different ways in how they subscribe to these multicast flows. Do they do what's called make before break, where they connect to the incoming feed before they switch over and then disconnect from the outgoing feed? Or do they have a limitation on bandwidth, and it's not possible to send two signals down the connection to them simultaneously, so they have to break their unsubscribe from the multicast before making the subscription to the new one? And again, that can cause some either still frames or potentially even a loss of their output temporarily. So again, how it behaves is quite different to SDI, and importantly, the time it takes is quite variable. I've seen quite a variation across different systems, and whether they can process multiple crosspoint requests in parallel. Introducing 2022-7 redundant flows again adds another level of complexity to this, and potentially more time taken to kind of set everything up. The fact that we're passing flows in 2110 as video, audio, and ancillary data as separate flows, again, just means that there's more to go on, which only makes things worse for the kind of delays involved in that IP fabric and how long it takes to respond and the receivers to respond. So it's yeah, don't expect instant switching with IP. And why does this matter? It kind of, to someone who's been working in broadcast for a while, it's like, well, obviously it matters. It's just expected. When we do routing in an SDI system, you press a button, you want that source to change then. What do you mean it's going to take half a second? And half a second is huge in broadcast. But what if it takes 2 seconds? I mean, that would be catastrophic in some productions. But again, if you don't specify what your system expectations are early on in the project and test suitably with simultaneous cross-point switch requests going on, you may find that you have to wait time, and you have people shouting at you because your system doesn't do what they expect it to do, because it's not an SDI system. And that's just something to be aware of. Again, everything can be worked around, but it just is, you have to be aware of it. So figure out where this kind of slow switching, even if hopefully, a vendor will promise you it won't happen, but what if it did? You can't, if they can't guarantee 100% of the time it will switch within 40 milliseconds of the request, then you have to assume the worst case. Look through your system, look through the operation, where would this have an impact? And if it has an impact, figure out an alternative solution, so that when you implement the project, if it turns out to be a problem, you can have a plan B. And that plan B might involve SDI, because if you really need guaranteed switching, maybe SDI might be the only way. So I thought I'd give a few examples of this, because this is an important point. One important thing that I kind of saw recently that wasn't implemented on an IP-based project, because there was no direct equivalent, was an emergency cut bus. So this is common. You'd find this is actually a photograph of an OB truck, an NEP's Aurora truck. You'll see underneath the vision mixer a little plastic panel, and underneath that a router control panel that controls an SDI router. And the idea being that if you had a failure of your vision mixer or some infrastructure around it, you could control the main output directly from controlling a crosspoint on a router in a very deterministic way. You could make your program, you treat it like a small vision mixer. All the sources are correctly timed, and therefore the switching is clean. Another place where you expect instant routing is in camera racking or shading, if you call it that. There's an operator sat in front of each of these racks, each of these 4 joysticks. When they press down on them, the monitor that's in front of them switches to show that selected camera. It is the job of that camera racking operator to balance the exposure, balance the kind of black level and the kind of exposure of the camera, so that as cameras are panning around, they all look about the same and they all fit within the gamut of the broadcast standard. They need to be able to switch between cameras instantly. They cannot cope or they will get very upset if you make them wait for when they're pressing that down. I've seen some operators who are constantly kind of pressing these joysticks up and down, and switching between cameras to kind of fine tweak things. Again, it's very important that the response is fixed and guaranteed. A more complex one to describe, which I hope I'll be able to get across the complexity of this, is a thing called virtuals, or what used to be called loop lines. Loop lines are a little bit old-fashioned, but the use of virtuals is kind of explaining loop lines explains where virtuals have come from. So let me try to explain what I mean by these. It's very common in a broadcast facility to have resilience. So you have a thing that's generating video and a backup copy of that same thing that's also generating the same thing. So if the main thing dies, you can fail over. And that's quite straightforward. You'll typically have some sort of control logic, or it may even be manual failover that controls a destination on the router to switch between the main thing, so the main thing's now live, and the backup thing. So whether the main or backup is live depends on the state of that cross point. And that's all well and good. We now have something going to air. That could be a playout system and a backup playout system. And again, you know, the good playout, the active playout system is the one feeding the transmission chain. What if you want other destinations that sometimes, not always, if they always wanted to see the destination, arguably you could use the same logic that controls the main destination. But if you just want to sometimes look at show me the main playout, how are you going to look at what is the main playout server? You need to know which one is the main one at that point in time, which one's the active one. And that's where loop lines can be useful. If we take a router destination, take an SDI, a coaxial cable, and connect it back in as an input, that then gives us a mechanism we can use to make routes from that source, that new source, to all those destinations. And then when we switch between our main thing and our backup thing, all three of those sources correctly follow the which one is active. And obviously, if these things don't want to look at them anymore, they can switch their route and switch to a completely different source. Nice and simple. Now, because loop lines were such a common requirement, and potentially on a project, you may want many tens, large system may have hundreds of them. Sooner or later, manufacturers of routers, and importantly, the control system vendors, made this work virtually, so that you didn't need to tie up physical outputs and inputs. It was a conceptual thing. So whilst you might visualize it in this way, what's actually happening is it's just tying the concept of those destinations together when they're all looking at that same virtual source. And in this way, you achieve the same thing, but you haven't got the cost of having any additional cross-point cards or any inputs and outputs of that router. So this is what I mean when I'm talking about virtuals. These are a virtual concept of a source or destination that you've created in your control system that allows you to route it to multiple destinations simultaneously and have that done automatically for you. You make one request for a cross-point change between the main and backup thing, and actually all those myriad destinations automatically switch to follow it. But that means in an IP system, well, the control system that understands the virtuals will be sending commands for many of these routes to be switched simultaneously. Now, previously, I've just said the predictability of cross points and how quickly they'll switch is quite variable in an IP system. It depends on the hardware you're sending the command to. It depends on whether or not the multicast that you need is on the local switch, or maybe it has to be routed through the system. A big problem here is if you're trying to switch the concept between main playout and backup playout, or main device backup device, you expect all of your devices to kind of switch simultaneously. And unfortunately, it's very unlikely, if not impossible, that they'll switch at exactly the same frame, which is what they would do in an SDI world. So an example of this is switching between different outside sources into a studio. You need to route that outside source to the vision mixer, the audio mixer, multi-viewers, different monitors in the monitor stack. Lots of different cross points need to be switched simultaneously. If you ever needed to switch between those sources live on air, that could be a problem, because the non-deterministic nature of when the switch will happen could be a major problem for the production. So a few other IP things before we finish off. Bandwidth. How many signals can flow down the same link? Again, there's been other presentations that talk a bit more about this and how the packet pacing and the kind of rate of the flow of the signal down the wire can affect this. One important thing to highlight, and I think Gerard mentions this in the network design webinar, if you have a 25 gig switch, you'll typically have 100 gig ports that connect to the main core switch or between switches. 100 gig Ethernet is actually 4 25 gig bearers. So if you're just using the standards-based approach to managing multicast, which is called IGMP, it doesn't have any cleverness to bandwidth, spread the load between those links, which means if you're unlucky, you may end up suddenly thinking on paper that your 100 gig link has the capacity for all of these cameras to kind of connect from one switch to the next, only to find that actually they all end up on the same 25 gig bearer, and suddenly you've overloaded your link and it all fails. And this is something, again, many people get caught out by. I know I certainly did when I was learning about IP. And this is one of the justifications for why you may want to consider using what's called software-defined networking. And this is where you put a management layer above the network switches that is more aware of what's going on in the system. And rather than relying on standards, IP standards for managing the multicast propagation, you have it directed by a software system. So this software-defined networking. And there's many vendors who will offer this, and the features that they offer may vary quite significantly. Importantly, though, they're all going to have to do some maths. How much bandwidth does source A to destination B, what does that require? How much bandwidth does it need to reserve conceptually across those links? Does it have any way of knowing whether or not, if it reserves a 3 gig link, because it assumes it might be 1080p 50 going down the wire, down that link, does it have any way of knowing if it's actually using that and if it needs it? NMOS, that might help, because again, the sender might be able to advertise what it's actually doing when it changes different resolutions using NMOS. So maybe that is a kind of future. But these are all still quite early on. But these are questions you should be asking about how it handles these kind of decisions. An obvious example of this is an edit workstation. I've put HD and UHD kind of data rates there. Again, lazily using the SDI data rates because it's the easiest to kind of think about. It may be. It seems unlikely nowadays, but what if you're using SD? That's an even lower bandwidth. How does it reserve 12 gig just because it's a UHD capable edit system when actually you might only need 1.5 gig? Isn't that very wasteful? Suddenly you've had to buy a much more expensive network router and all the kind of link capacity than you'll ever need. Can you work out what you'll ever need? Will you have to kind of work out some kind of rough approximation of how many of your edit suites will ever work in UHD simultaneously? These kind of questions need to be asked. And it's not just about single links either. Lots of SDI based systems for UHD are using quad link. So 4 separate SDI connections. How does the IP system transport that? What if an editor is doing some graphics work and needs to preview things at full chroma resolution? So what's called 444. This is another case where it uses what's called dual link SDI. So 2 SDIs where the kind of signal is split between the SDI signals that must arrive in time with each other. So all these kind of questions, you have to think about how your system will handle all these kind of edge cases, because when you install a system, you'll suddenly find that your graphics people will say, what do you mean it can't handle 444? But we use that all the time in SDI because their hardware is directly under the desk. It never is an issue to anyone because it's just going over 2 meters of 2 SDI cables. Now you want to put it into a data center architecture and put their workstations in somewhere else in the building. So you just assume that they only need 1 SDI connection. Actually, they need 2. Who knew? These things are catching people out. A couple of other considerations. If you've got UHD production alongside HD, what happens if you've got destinations that can't handle UHD? What should you do? Should you stop it from even trying by prohibiting it in the control system? Is there some clever way you could route it automatically through some sort of down conversion device or something that would kind of legalize it? what if the device, as some UHD devices do, has a parallel HD monitoring output? So some devices now have a UHD output and the HD output in parallel. Can your control system cope with that? And can that control system communicate that appropriately to the IP fabric? Will that work? SD, that could complicate things. Again, in similar question about some devices not supporting HD devices not supporting UHD. I've seen some new UHD monitors from Sony that don't support SD, for example, which again catches you out. It's probably not an IP problem, but it's something to be thinking about. And PTP, what is there to say about that? It's probably best we move on from that. PTP is a whole can of worms. I think every project that I've heard case studies talk about and spoken to people about, PTP's always been one of the areas that has just absorbed time. Engineering investigations into problems with failover and troubleshooting things not quite working. Again, get help. Talk to the vendors who have got the experience of doing this and try to do what's been done before. And again, I think Gerard says a bit more about that on his webinar. And if you can, test it as much as you can. Try and get kind of mock-up systems. Try and test the scale if you can. It's really important. So again, I realized looking through that, I could have added more things. There's a whole can of worms around configuring IP-based systems. What about all the different multicast addresses that need to be put in there? At the moment, people are using big spreadsheets and manual entry of these kind of IP addresses. Lots of scope for things to go wrong. Over time, systems will get better. Automatic configuration will get better. A lot of work's being done in the kind of under NMOS, and the EBU's got their kind of pyramid that talks about some of the kind of things that IP media systems need and looks at security and aspects like that. So there's a lot more to learn. So this was just a taste. And then I did say, why will SDI never die? And I kind of mentioned it earlier. It's the perfect firewall. If you need to get signals between areas, SDI is ideal. Even contemplating connecting up one IP system to another IP system, you just don't want to be going there. It would just be a nightmare, not from just the configuration side of it, but also the risk of linking two IP systems together and the potential for propagation of viruses or hacking attempts. Which is why one area where SDI is still being used as well is on a lot of the latest all IP OB trucks. You'll actually find a lot of IP to SDI interface cards, so that the handoff point to an adjacent truck or an adjacent system that they need to connect into, that might be still SDI on the kind of backplate of that truck. So again, I think we're going to see SDI around for quite some time. So that's it. I hope I've not been too pessimistic about some of the IP things, because like I said at the beginning, IP really is the future. Every problem that we've identified, if it can't be overcome, it can be worked around. It can be overcome by working around it or by changing the way people operate. But don't expect it to be a direct replacement for SDI. Video over IP is its own thing. We have a new phase of broadcast engineering to learn all about it and learn all the foibles of it. We're in the early days. The early projects, they are certainly going out there now. Projects are going live. It's being successful. So I think the future of IP is certainly there. So thanks for your time. I hope it's been useful, and I'll look forward to speaking to you soon.